Yeah.
All right. Well, we are at 7 o'clock, or well, Eastern time. So
You can't even say the top of the hour because for some people it's the bottom of the hour.
right.
And for people in India, it's the middle of the hour.
Well, that's what I mean by bottom of the hour.
That's what he meant.
Oh.
Yeah.
Oh, okay. Okay. Yeah.
Okay. Well, let's. AC, you want to get started?
Certainly. This is LSR and the last meeting of IETF 111 online. Next slide. Okay, I'm sure you've all seen the note well. Basically, the crux of it is that if you know about IPR and you're participating in any manner, you're compelled to disclose it. You can read the details here. Next slide. Okay, 1 RFC. Next slide. Since 110. Okay, we have these three sitting here in cluster 340. I'm not sure what they're waiting on because there's no dependencies on any of these on any, there's no misrefs or anything, but these are going to come out shortly as well. They already have numbers. I just didn't put the numbers in the status. So we have three more that are going to come fast. Next slide. I saw that Tom Petch nudged John, and he talked to the RFC editor. So maybe now that this BFD Yang reference to the TE model is resolved, is removed, not resolved, maybe we can get all these protocol Yang documents published. That would be good, just to have them with the RFCs. And next slide. Let's see here. Yeah, we finally got the ISSRv6 extensions. It should go to telechat. I mean, it's under IESG evaluation. We have some maintenance drafts. Flex algorithm, we did the second last call, and the discussion resulted in a errata to 8920 and 8919. Hopefully that one will get through 80. You haven't looked at that one, John, right? You haven't looked at Flex algorithm, right, John Scudder?
He's coming.
Right, I have not. I've got some backlog in my queue that I need to plow through,
Sure,
but
okay.
I'm aware of it and I'm going to do it.
Next slide.
Sorry.
This one is also waiting. It's a lower priority, I think, though.
Yep.
Next slide. This isn't working with last call. I saw another IPR just recently, but I realized it was just a refresh of the old one. I don't see anything different. I'm going to look at that closer next week, but I think it's just the same. And IPR that was issued at the onset of the document. Next slide. Let's see, is there any here that... Yeah, we have all these Yang models that we believe are ready. They augment the base ISIS and OSPF Yang models. Next slide. Okay, we're going to cover the flood reflection today. This is an experimental draft, and Tony's going to talk about it. We started a list discussion. Strict mode BFD, we should be able to do that one. There's actually implementations to that one. And OSPF v3 for SRv6. That's a rather complex draft. We want to make sure we get it right, but we'd like to get that one as soon as possible and ensuring the quality because it's a normative reference to it in Flex algorithm. Next slide. And let's see if there's anything worth talking about. Reverse metric isn't being implemented by anyone. It's not a real high priority, but it's basically ready as well. Next slide. Let's see if there's anything here that needs to be really, no, these really haven't changed since last IETF. Next slide. Next slide. You can see those. We're going to cover the flex algorithm bandwidth. We'll have a discussion of that. It's going to be covered today as well. Specifically the generic metric discussion. Next slide. And we have a couple in adoption call. And then we have people who have asked, I'll wait for it to move. We have people who have asked for adoption, and these are all on the agenda today, so I won't say anything more. Okay, I think we're done. I tried to go faster than I had in the past, so I didn't go through every draft. I just looked for the ones that I thought I needed to make note of to the working group.
Okay.
So who's going to go first? Is it Bruno or Les?
What do we have up first? Sorry. You have Les up first. I'm going to try resharing to see if I can share just the application.
Okay.
Can you guys hear me all right?
Yep.
Yes.
I'm going to have to put on my glasses to look at those graphs.
All right.
Actually,
So,
I'm going to turn off my video now that I'm done talking to it.
all right. So let's get started so we can leave a good amount for the open discussion. Next slide, please. So the changes that we made since the last significant revision, we had an example algorithm. We removed it for a number of reasons. One, we've actually worked on an implementation now, and our implementation was not identical to the example algorithm. The algorithm is in any case a local matter. There's no interoperability issues, so people could implement things in different ways and it would not cause any problems. So we decided to replace the example algorithm with a few broad guidelines that anybody who implements the algorithm should follow. Next slide, please. So here are the basic guidelines. We note that flooding burst durations are not that long-lived in general. For example, if you needed to flood 2,000 LSPs, for example, a node with 2,000 neighbors goes down, and you were flooding at 300 LSPs per second, this takes roughly 7 seconds. So this is something that needs to be taken into account in terms of your response time. If you're not going to respond to adapt to some change in the capabilities of the receiver, and you only do that every 30 seconds or every 60 seconds, it's not going to be very helpful. We expect that receiver performance is not a constant, that it may be affected by transient conditions, bursts of packets from other protocols or data traffic or OAM traffic or what have you. So we need to be able to be adaptive. And our goal, one of the goals is trying to minimize retransmissions. And again, this is another reason why we want to have a fairly quick response time, certainly less than 5 seconds. Algorithms should be more aggressive in slowing down when they detect a reason to do so. and less aggressive when speeding up. And we want to work with both enhanced nodes and legacy nodes. So, there's been some work to demonstrate, for example, that sending ACKs more quickly is an aid to faster flooding. But, there are nodes out there that don't do that, and we'd like to be able to interoperate with them. There are a number of other flooding optimizations that people might have implemented. They may do parallel link suppression. They may implement the dynamic flooding draft. We want to be able to work regardless of whether these enhancements are being used or not. And we've also had discussions how implementing packet priority, for example, processing SNPs at a higher priority than LSPs, so you process the ACKs more quickly as a help. But again, if the neighbor hasn't implemented this, we still want to be able to do faster flooding. Next slide, please. So this is just a very high-level overview of our proof of concept implementation. We're not going to go into all of the details of the implementation. What we do is we track the rate of transmissions and we compare it to the rate of acknowledgements over a multi-second history. And if the two of those are not in sync, then we're going to adjust our transmission rate. There are two parameters that need to be configured, only two. One of them is what's the target maximum transmission rate that the customer wants in their network. This is a per node value. We refer to this as LSP-TX max. And we also want to know what the receiver ACK delay is in milliseconds, which is a per neighbor value. This is so that if somebody is, for example, by default, or at least by specification in 10.589, the PSNP ACK delay is 2 seconds. People may be using that. They may be using something faster. And knowing what that delay is helps the algorithm determine whether the receiver is keeping up or is not keeping up more accurately. So we incorporate that into the algorithm. We are agnostic to the reason for the delay. Packets could be lost on transmission. They could be dropped on ingress to the receiver node or being punted from the data plane to the control plane. There could be CPU issues. ISIS may not get to run as much as it would like to. Doesn't matter to the algorithm.
Hey, Tony was on the queue.
He was in the queue. So the question first is, Les, do you want to hold questions to the end or do you want to be interruptible?
Well, partially I think this is up to you guys, but I would kind of hope that we would hold questions because we do have an extended period for open discussion, and okay. I think that would be better. That would be my preference anyways.
Yeah, so unless it's an immediate, just clarifying question, let's hold questions until the end because we have dedicated over a half hour to discussion. Okay.
Okay. And just a note, the current flooding rate is referred to as LSP-TX rate, as opposed to the target maximum, which is LSP-TX max. I'm not sure that we incorporated that name on all the slides. I apologize for that, but just to clarify the distinction. Next slide, please. Here's the basic test topology. We have an emulation of a large network so that we can get most of the tests were done with 2000 LSPs. So that's just a simulated network. And then we have a sender, which has implemented the algorithm. And we have a receiver, which is fundamentally unchanged code. The only thing that we have done on the receiver is we put a hook in to artificially manipulate the receive rate that the receiver will support, so that we can test when the receiver is able to, for example, handle 100 LSPs per second or 300 LSPs per second, and so forth. But other than that, it's base code. Both the sender and the receiver are real hardware platforms. And the basic test procedure is to reset the receiver. We now have to sync the full LSP database to the receiver, and we're measuring the performance based upon that. Next slide, please. Just a little explanation about, you'll see a column related to the LSP transmission strategy. When you're sending at a fairly slow rate, as historically we have done, it's reasonable to say, for example, if I'm doing 33 LSPs per second, I can expect that I will wake up 33 times a second and send 1 LSP each time. But at higher transmission rates, it's unrealistic to expect, for example, we're going to wake up 1,000 times a second and be spot on each millisecond. So we keep track of this, and if our goal, for example, is to send 1,000 LSPs per second, we recognize that we're going to wake up at some slower rate, and we're going to send some burst, and depending upon the CPU load at the moment, the scheduling rate may not be perfectly linear, and we try to adjust for that so that the net is that we are sending whatever our target rate is per second. We refer to this transmission strategy as optimized. You'll see the term optimized and base in the data that we show in the subsequent slides. Next slide, please. So here's just a baseline. There's no operation of the actual algorithm itself, other than the optimized transmission strategy that I was discussing on the previous slide. And this just simply shows how long it takes to transmit 2,000 LSPs at the given rates. I think there's nothing very surprising here. Next slide, please. All right, so here's an example where we're slowing down. Again, we have 2,000 LSPs to flood. We're starting out with a LSP TX rate of 300 per second, and the receiver is actually only able to handle 100 LSPs per second, and the transmitter has to slow down. So you'll see with the two baselines where the algorithm's not in use, the second line is probably the most instructive here. We're trying to send roughly 300 LSPs per second, and we're just doing so blindly without regard to the performance of the receiver. And you see that we end up with a very large number of retransmissions. We then have two cases where the algorithm is in use. So our starting LSP TX rate is 300 LSPs per second. We're going to have to adjust that based upon how quickly we're getting ACKs back from the receiver to adjust to the receiver's rate, which is 100 LSPs per second. And you see that what happens is we get a lot fewer retransmissions. There's a similar test case where our initial rate is 1,000 LSPs per second. And again, we've got to adjust down to 100. There you have a larger number of retransmissions because initially we're sending much faster, and it takes us a little bit of time before we realize that the receiver is not keeping up. If we go to the next slide, you'll see this in graphical form. So the left-hand graph is showing the results from adjusting from a rate of 300 LSP second down to the receiver's capability of 100 per second. And you'll see that it takes us about 3 seconds to adjust to the receiver's rate. The graph on the right is in the case where we're at 1,000 LSPs per second and we have to adjust down to 100. It takes us a bit longer to adjust from 1,000 down to 100. It takes us somewhere between 4 and 5 seconds. And that explains why we have more retransmissions. Next slide, please. This is an example where we're at steady state and there's no adjustment required. If we go to the next slide, this is just to demonstrate that we're not oscillating up and down. We're just staying at the last known rate that we knew was good. And so we have no retransmissions here. Next slide, please. All right, here's a case where we're speeding up. So we're starting out at a rate of 100 LSPs per second, and we've altered the receiver's capabilities so he's not limited. And we see that the sender has to adjust to the new rate that the receiver can sustain. And again, we have 2 examples where the algorithm is in use. One where the LSP-TX max target is 300 LSPs per second, and one where it's 1,000 LSPs per second. You'll see, before we go to the next slide, I'll just mention on line 4 that the adjustment from 100 to 1,000, because we ramp up more slowly, deliberately, it actually took us multiple bursts before we actually reached the maximum of 1,000. So if we go to the next slide, we'll see that in graphical form. So again, the left-hand side, we're adjusting up to from 100 to 300. And you can see that we hit the maximum rate in about 11 seconds. The graph on the right, we're trying to ramp up to from 100 to 1,000. And you can see that it took 2 bursts. The first burst got us up to about 500 LSPs per second. And the second burst got us up from 500 to 1,000. Next slide,
Tony
please.
P has on this chat has mentioned a couple times that he thinks that should be TX transit,
Yes.
I think, instead of
yes,
max.
No, he's absolutely right, and I apologize for that. I'll apologize for it again. The blue line is labeled LSP-TX max, but it should be LSP-TX rate. In other words, the current rate at which we're sending. He's quite right. Thanks for pointing that out. I apologize.
Yeah, I just wanted to do it during the graph because I'd forgotten
yes.
what you said earlier.
Yeah, no.
Okay.
No, thanks, Tony. Okay, next slide, please.
Units of time are point are a tenth of a second.
No, they're seconds. You can go back to the previous slide because this is actually the last slide I'm going to present. Yeah, these are seconds. So in fact, if you go back one more slide, Chris.
There we go.
Okay, so you can see the total elapsed time in milliseconds. When we go from 100 to 300 is a little over 11 seconds. In the case of going to 1,000, there's actually 2 bursts. The first burst took us about 10 seconds. The second burst took us another 3 seconds. Does that, AC, does that help clarify for you? All right, you're muted, so.
So you could put a comma there. I was
Yeah,
curious
comma,
about
slash, whatever.
Yeah,
But that's
yeah,
why I
right.
say,
Okay.
all right, again, if you go one slide ahead, you'll see there were 2 bursts involved to get us all the way up to 1,000 if you look at the right-hand graph. So we sent
Right.
2,000 LSPs, we got up to about 500, and then we waited a little while, and then we sent another burst, and that got us up to 1,000. And that's all I wanted to present at this point. There are some other slides which Chris and AC, I'll leave it up to you whether you want to use those as talking points in the discussion period, but that's
Okay.
it for me at the moment.
All right, that sounds good. Yeah, let's go to the next presentation, unless somebody has something they think should be clarified before that. Okay. Not switching in the thing.
Okay, hello, can you hear me?
Yes.
Okay, so hello everyone, I'm Guillaume Solignac. I'm here to present you the work we did with Bruno on flow and congestion control for ISAS, and especially on the basis of the draft. Next slide, please. So the first point we want to clarify about the problem is that there are actually two problems that we are trying to solve. The first one takes place in the control plane, namely in the IS process and the socket buffer, or the input queue before the ISAS process. And the other part of the problem is the path between the ingress and this input buffer. Next slide, please. And so we argue that flow control is used to deal with the problem of flow control, of CPU contention, while congestion control deals with congestion inside the I/O path inside the router. Next slide, please. So the goals we are trying to achieve, well, they are pretty much what Les said just before. We are trying to achieve faster flooding, especially when the receiver has 3 cycles, slower flooding when the receiver is busy and congested. We also want to avoid or minimize the number of parameters the operator has to tune. We also want to minimize the loss of LSPs. We want it to be reduced to a wide variety of conditions, and bonus point for the simplicity of implementation. Next slide, please. So the first part studies the impact of the Arwin algorithm described in the draft and how it achieves flow control. Next slide, please. So the goal is to avoid losing LSPs at the receiving side, and in particular at the control plane. The draft focuses more on point-to-point interfaces. And for this, there is a classical algorithm, which is to use a receiver window, which we call Arwin in the next slide. And basically, the sender will never send more than Arwin acknowledged LSPs. So you can see the algorithm summed up just after. And this asks 2 changes to the protocol to make it work. The first one is to advertise the receive window inside the Hello PDO. And the other one is to change the PSNP behavior to get faster feedback. So if I want to give you a small example. For example, in that case, Arwin has the value of 6. So the sender will send 6 LSPs, then wait, because it considers that the receiver window is filled. The receiver will process the LSPs one by one and send the PSNP. And the sender will send new LSPs once it has received the acknowledgements. So this way, there is a natural pacing to the receiver acknowledgement rate. Next slide, please. So there have been some questions on how to choose Arwin. Well, so we assumed that there was one socket per neighbor. So in that case, you can use a socket size divided by 2. So there is space for other PDUs. If in your implementation you have an input queue that is shared between neighbors, you can advertise this size divided by the number of neighbors, so that every neighbor gets a share of your receive buffer. If you don't have access to this information, but I think that should be the case in every time, you can use a TCP value, which also uses a receiver socket. And in the worst case, you can still use a conservative value of 10, since well, a popular implementation already uses considers that bursts of 10 LSPs are doable for a receiver. I want to stress that this is a software parameter, since we just look at the input queue size. This is totally hardware independent. We really don't care about the IO path in between the control plane and the ingress. Next slide, please. So when to send the PSNP, we reuse the mechanism that was presented in the previous IETF. The receiver chooses a parameter LPP for LSPs per PSNP. And so once it has LPP LSPs to acknowledge, it will send a PSNP right away. The other way is to send, to trigger a timeout, a short timeout, that will trigger the sending of a PSNP if the PSNP does not reach LPP. Next slide, please. So the algorithm Arwin relies on one static information, the size of the socket buffer. There are multiple identified parameters that influence its behavior. There is, of course, the value of Arwin advertised. There is also the RTT, which does not appear in the algorithm explicitly, but has an impact on the theoretical rate you can achieve with this algorithm. And the other one is the LPP value that has an impact on performance, as we will show afterwards. So if we want to look at the theoretical rate we can achieve, it is Arwin over RTT, because in the best case, you send Arwin LSPs, you get the acknowledgement right away. So you can send Arwin LSPs every RTT, which gives you a rate of Arwin over RTT. Next slide, please. So the experimental setup is pretty much the same as what was seen in the last presentation. We have a router with a large LSP database. We have a router with an empty LSP database, and we establish the adjacency between both and see what happens, see the reach sending rate. Next slide, please. So here you can see the results for two different LPP. So you can see the parameters on top. And so you can see that the achieved rate is close but lower than the theoretical rate we could achieve of 2,500 LSPs per second. And the other very interesting part is that there are no LSP losses. Next slide, please. So this is the same experiment with a larger RTT. And so here again, you can see that we are close and even closer to the theoretical rate than the case before. And again, there are no LSP losses. Next slide, please. So if we want to look at why there is a difference between the theoretical rate and the two actual experiments, we can look at the time an LSP takes to be unknowledged. And this is the graph you can see on the right. On top for LPP equals 5, on the bottom for LPP equals 15. And you can see that the actual measured RTT is higher than the 20 milliseconds we set up on the link, which explains why we have a lower actual value in part. And so this is due mainly because of the computation time, processing time of LSPs. The other important point is that Rwin should be a multiple of LPP. Otherwise, there is unfilled PSNPs and LSPs get buffered, like it's useless to buffer them, and it actually makes the effective Rwin lower than it actually is. Next slide, please. So there have been some concerns about what happens when we increase the sending rate, because it means more stress on every part of the router between the ingress and the control plane. And so we wanted to study what happens when multiple senders are actually sending to a single receiver. So next slide, please. So this is our experimental setup. Instead of having one sender, this time we have 10 senders that send their LSP database to the receiver. Next slide, please. So here you can see plotted on top the bandwidth achieved by every sender, so one color per sender. And on bottom, you can see the metric I talked about before, which is the time an LSP takes to be hacked. The three graphs correspond to three different Rwin values. And we can see, well, surprisingly, that it reaches around 2000 LSPs per second in every case, while we expected that by doubling the Rwin, we would double the rate. And the explanation is that we are actually in a CPU-bound case. And so it's very interesting to see that the Rwin algorithm pays naturally to the CPU processing speed. The impact of increasing Rwin is thus to increase the latency the receiver takes to acknowledge PSNP, since LSPs get buffered for a longer time. Again, two good points. There are no LSP loss again, and the senders pace well to the receiver. So it's 2000 total. It's around 200 LSP per second per VLAN, which gives around 7x speedup compared to the default rate. Okay, next slide, please. Now, we wanted to study what happens when there is I/O bottleneck. So when there is no information available at the sender side to deal with an I/O bottleneck. Next slide, please. The experimental setup is the same. Next slide, please. So the difference is that instead of having a very large link between the two machines, we have a bottleneck of 10 megabits per second with a large buffer for this link. And you can see the results on the right. The senders managed to fill the bandwidth link. And there is no LSP loss. This is no surprise because the sum of the Rwin of all the senders are actually smaller than the bottleneck buffer, which prevents losses from happening. Now, we wanted to see what happens when the buffer is smaller and that there are losses that happen due to I/O congestion. Next slide, please. So now we reduce the buffer size to 64 packets. And there are unsurprisingly losses. And you can see the losses on the bottom graph. They occur every 5 seconds. These 5 seconds correspond to the retransmit timer, where a sender considers that an LSP was indeed lost in that case and comes back to the queue for retransmission. The other interesting point is that we completely fill the bandwidth during almost the duration of the experiment. So there are around 10% losses on the total of LSPs transmitted. And the losses correspond to the difference between the sum of the receive window with the buffer, the bottleneck buffer. Next slide, please. So next, we wanted to see what happens when we try to increase a bit more slowly the rate of transmission. So instead of having directly Arwin unacknowledged LSPs that are allowed to be sent, we increase it gradually from 1 to 50. And this has the effect that you can see on the bottom graph, that losses get a bit spread out. So it helps mitigating a bit the burstiness. So we can see that it's arguably not enough. So next slide, please. So yeah, if we want a bit to sum up what we have seen so far, there are 3 sending rates possible. In the first experiment, it was the Arwin limit. In the second experiment, it was the CPU limit. And in the third one, it was the IE limit. In every case, the algorithm managed to completely fill the bottleneck. And the other very interesting lesson is that the first 2 cases cause no LSP losses at all, because the way it is designed, there cannot be losses due to CPU contention, and of course, if we reach the Arwin theoretical limit. We think that CPU will be the bottleneck in many implementations, and that's why it makes sense to add the Arwin algorithm in implementations. So the only problem that is tackled by congestion control, whether by our proposed algorithm or the one proposed by LESS, is the IO bottleneck. Next slide, please. So again, a recap of what we gained. The cost is a new TLV, knowing the size of the socket buffer, and more PSNPs to be sent to be able to benefit the more from the algorithm. The gain is that there are no LSP losses due to CPU contention. The speed is paced by the receiver axe, and the dropped LSPs artificially fills the receive window on the sender view, which means that internal congestion still has some good properties, even in case of internal congestion. Next slide, please. So here we added the congestion control algorithm on top of our Arwin algorithm. Next slide, please. A small recap on how we do congestion control. I think I will skip this part since it's not very relevant to the discussion. We can go afterwards. We can go back afterwards if you're interested. Next slide, please. And so here you can see the results of our algorithm with the same benchmark as before. And the congestion control algorithm actually helps a lot in avoiding this spurious retransmission that we saw before. And we go from around 10% to 1% of lost LSPs. There is a large overshoot at the beginning because we are aggressive in the starting phase. And this aggressive phase called slow start could be removed like we saw before, but it helps in scaling to larger links because being more aggressive allows to reach larger sending rates. Next slide, please. So why not why don't we do only congestion control like proposed just before? It is very likely that there is CPU bound at some point in the life of the IS process. So for many reasons, it can be another process can be scheduled. There could be expensive SPF computations. And in that case, the Arwin algorithm deals perfectly, since all the send LSPs can be buffered before being processed. The other problem is that congestion control, if not bounded by a flow control algorithm, will consider that CPU slowness is actually congestion, while it is not. Packets could be buffered since we could know the space available to store them. And the other point is that they can work together. In our case, you could perfectly use Cwin algorithm and then add the Arwin algorithm on top. And I think it could be interesting to see the results of less with adding the additional guarantee of Arwin. Next slide, please. So here is a recap of all the results, and we can see that in the CPU bound case, the Arwin algorithm deals perfectly with the problem. Next slide, please. So yeah, we achieved many of the goals that we set before. Next slide, please. And I think I will stop on this slide since the time is expired. The Arwin algorithm only deals perfectly with CPU congestion. It does not deal with IO congestion perfectly, but we still have some guarantees. And congestion control algorithm only has a partial effect on CPU contention, even though not perfect, and deals very well with IO bottlenecks. Well, thank you for listening. And yes, I think we can have the discussion now, if the chairs allow it.
Great. I've been collecting some questions. There's been a lot of talk in the chat as well. I don't know if we probably want to bring some of those back in. Let me pull up the questions on your presentation first. One of the questions I had overall was, and maybe we can go back through the slides, but how much faster was yours with Arwin than with the congestion control, with Les's proposal? Do we have a comparison?
Well, I think it's hard to be fair in the comparison, like comparing flow control algorithm and congestion control algorithm. I think I'm not sure if the comparison is very relevant since they deal with.
No, but what I'm saying is, well, it has to be relevant. It's the point, right? What I'm curious about is, and maybe we can do this right now and figure it out, but how do as an audience, when we're looking at these results, how much faster is it going to go, right? That's the goal, right? Is that we flood faster, and we have results. There were some results we can go back to in Les's where it showed, like 17 seconds, I think, or these different things. Is there some number that we could say? Have you guys looked? You guys looked at each other's stuff, right? I mean, is Arwin like? Does it get everything done in 3 seconds for 1,000, or whatever? So
I mean,
yeah.
Yeah, I think I get your question. The Arwin algorithm alone, I think we don't want to use it alone, even though that's what we showed here. I think we want to see the receive window as an additional guarantee on top of congestion control algorithm. And this way, the congestion control algorithm cannot lose packet due to CPU contention. Because as soon as the Arwin algorithm will hit some IO bottleneck, it will lose packets and potentially perform way worse than a simple congestion control algorithm would have done.
So one of the things I wondered is Arwin the equivalent of making Less's transmit max dynamic? Is that?
Yeah, indirectly, yes, because by
Okay.
bounding the number of buffer packets, you will bound the transmit rate, and you don't
Okay.
have to take an arbitrary value.
Yeah, no, I want to be, I've got more questions, but I want to be fair to the people in the queue. So,
Yep.
Bruno, are you next?
Yes, thank you. Trying to answer your question, Christian. Indeed, it's difficult to compare the raw number because hardware is different and implementation are different. But if you are CPU bound, if you just use Arwin, the sender adapts exactly to the capability of the receiver. So if the receiver can process and acknowledge 312 LSP per second, the sender will send 312 LSP per second. So it's a maximum that can be handled by the receiver. If the receiver pause, so for example for 300 milliseconds, the sender will pause by 300 milliseconds. Again, same number. For any change in the behavior of the receiver, the sender will adapt quickly in one RTT and with no loss of LSPs. So it's important to compare how fast you adapt on how many LSPs you lost on the process.
Yeah, Tony P in the chat is bringing up that I shouldn't have said max. I think I should have said the target. I don't know. Actually, maybe Tony can come and say that at the mic. Okay. Yeah. So, and again, I think I'm taking from that, unless I'm wrong, that there's a target in a fixed target unless maybe you can. Is that the case? There's a fixed target in your case, and in the Arwin case, it's a target set by the receiver.
So first of all, I want to reinforce Bruno's point. You can't compare raw numbers here because clearly we ran this with, different hardware
Right.
and different implementations of the protocol itself. So I don't think that's fair. I think the more relevant question is which one of these two is adaptive. As I understand this, and I'll let Guillaume and or Bruno respond, but based on the email exchange, they're not expecting to modify Arwin dynamically. It's chosen at startup, and that's the number you get. So to me, this implies that you have to pick a number that's conservative because you want it to be able to work even when the receiver is very, very busy, perhaps not with ISIS, but with other things. So that I think is the point I'd like to discuss.
Right, but it's also something that could be easily adapted, right? I mean, when we talk about the R window and the value, it totally reminds me of credits, right? It's like, so we could just change it to a credit space thing where the receiver says, okay, your window's this big now, and you can adapt that value based on the receiver.
Again, I'll defer this to Guillaume and Bruno, but I just want to get that point clarified because as I understand it, it's not adaptive. And in order to be adaptive, I think there are other inputs that they need to get, which are difficult to get. But let me turn it over to them.
Yeah, let's go to them. We can come back to the inputs.
Yeah, so there are really two things, the Arwin and the congestion control algorithm. And the Arwin is really the upper bound on what can be stored before ISIS processing. So we really think that all in all, you will need both a congestion control algorithm and a receive window to get the best conditions you can have. So in our case, the signal we have to deal with congestion control is not the same as LESS, which monitor the acknowledgement rate. In our case, we use a variation in the, well, we monitor if an LSP gets delayed for too long compared to the usual rate. So the dynamicity of the sender comes from the congestion control algorithm. The receive window is just a guarantee on top that you will not lose packets due to CPU contention. I hope it clarifies the point.
Okay, and I want to go to, I think, Tony next, unless Bruno, let's let Tony go maybe, and then we can come back to you, Bruno.
So I'd like to just redirect and have people think about this as a control loop problem. And the specific implementation here is certainly open for discussion. But the point is that if we have feedback, if we can give information, and it probably would be best if it's real-time information, back to the transmitter, we can do better. Right? If we take a look at Les's slides, it's very clear that there is some time for the transmitter to react. And maybe we can improve that time. That's all.
I have to say, by the way, this is all for me as a but I agree with you, Tony. I think that it's a good starting point. I'm not allergic at all to adding information. You know, I think that there's been some people are interested in not adding things because, you know, I don't know why, but you know, I'm not. I don't have that aversion myself, and I think that so many other, you know, rate limiting and or improving things include feedback, right? So I don't think we should be so averse to it. I agree. So Bruno, do you want to go next?
I just wanted to clarify the question from Les. The window is static, but the window does not express the rate that we're going to achieve. The rate is determined by how fast the receiver will process and acknowledge. So I'll try to give an example. If I say, well, please state one sentence one by one and give me some time to process, the rate of the sender, of the speaker, will be limited by my time needed to process the sentence in English. So if I acknowledge in 2 milliseconds, you can send one sentence every 2 milliseconds. If I need 10 seconds to write it down and understand it, you can send one sentence every 10 seconds. So the window is static. The rate is dynamic based on how fast the receiver can process the LSP or the sentence.
So another question that I had was because how related is the TX max value in Les's proposal to the R window? Those are both static values, right? Are they also serving similar goals? Les, maybe you can go and you can also clarify that whatever you wanted to clarify.
I think that the answer to your question is probably a qualified yes. But the TX-based algorithm is built to adapt. As I understand the RWIS-based algorithm, you pick a number that is never going to change, and it's not going to adapt. So the behavior that you get from RWIN is because the receiver goes, okay, I can send 10 LSPs or whatever the magic number that has been advertised is, and then I have to pause. And I have to wait in order to get the X. And I think in both of our cases, the testing that has been done thus far is somewhat artificial because we're only running ISIS. And in fact, we're only running it on our limited topology. We don't really care about updating the fib and all of this stuff. But in the real world, of course, we're going to have a large network. We're going to be running other protocols. We're going to have data traffic. We're going to have OAM traffic, what have you. And the capabilities of the receiver are not going to be static.
You simulated this though, didn't you? You actually put the limit on the receiver of 100 LSPs.
Yes.
So you were
Yes.
simulating that condition.
We did simulate it in a simplified way, and that's to demonstrate that the algorithm does adapt. It obviously doesn't adapt. In the case of Solidon, it doesn't adapt with 0 retransmissions, but it does adapt. And I think this is an important aspect of whatever solution we pick, because obviously, in the real world, we're doing a lot more than just ISIS processing.
Okay. Guillaume?
So I was reading Tony's point, but I agree that you need congestion control, and the value you advertise is really not magic at all. It is the space you have before CPU, your LSP gets actually processed, and I don't think it's too much to ask to have this value. I think the buffer you have just before where your LSP gets stored before processing. So it's really no magic. I agree that this RWIN can become a bottleneck, especially in the case of large RTTs. But in the example I sent on the mailing list, for example, if you are able to guarantee a buffer of 10 LSPs, and you have an RTT of 10 milliseconds, say, you are able to reach 1000 LSP per second. So actually, it's very likely that if you have a buffer large enough, you will never reach this bottleneck. So you actually need a congestion control algorithm. I very agree with this again. And yeah, sorry, I lost track, but
okay,
yeah.
well, let's move on. Yeah, that's okay. Tony?
The current stuff that was just presented, RWIN is static, but let's remember that's not set in stone, right? We're out with a proposal that does what we want, and we don't have to pick and choose A or B right now. So the point that we're trying to make here is that feedback is helpful. And in a perfect world, we could instantaneously tell the transmitter what Rx max is all the time, right? That would give us the perfect transmission rate under all cases. Now, we practically can't do that. So then the question is, how fast can we signal and what can we signal? I'll step back.
Bruno, you can go. I do want to get Catan. He's new in the queue, but go ahead, Bruno.
I agree with Les that we want the sender to be dynamic, to adapt to whatever happens. So maybe a RIB update, BGP computation. But again, that's exactly what provides RWIN. Again, if the receiver stops for 200 milliseconds for whatever reason, then the sender will stop for 200 milliseconds exactly after a period of 1 RTT, but without losing any LSP. And it's a clear difference between both proposals. We can see that we can adapt to different rates, different number of neighbors, without losing any LSPs for the two cases where it is CPU bound. Whereas when if you do just congestion propose, we can see in the slides from Les that it adapts very good, but after a loss of LSPs, it's because that it reacts to the bad news. So I think it's a key difference on both adapt, but I think one adapts faster and without loss of LSPs.
Okay, Ketan?
Yeah. So at least what I kind of learned or arrived at is in practice the Arwin window is more or less like the max TX rate which is in the other proposal, more or less so. And the point is, if Arwin is static or constant, then I really don't see it as something that is a max rate configured, let's say on the per link basis kind of thing on the receiver on the sender side, right? Where I see the key challenge, and I think that's what I'm hearing as well, is for this mechanism or Arwin to be really effective, it needs to be a dynamic value. If it is a static value, then I'm not really sure how it helps this thing. Even if it is a static value, let's assume I do not know how that can be determined, and maybe there were some assumptions on there being a socket per neighbor or interface, and all of those. There were some other assumptions. Maybe take the value from BGP and things like that. So those
Okay, well, we're almost out of time. I think your point is made, and I think other people agree with you, right? That this is dynamic is worth exploring here.
Yeah, I think that's probably what I'm saying is that's the one which would really make a difference. And the next part is last thing is that there are these assumptions, there are these additional requirements that are needed to implement this, and they all would be helpful if they are documented in both the proposals, right? What is the backward compatibility? Do we need it on both sides? What kind of implementation assumptions are need to be factored? If they are captured, then that will help in a better analysis.
Great, that's a good idea. Les?
Follow-up points. One, I agree with Tony Lee that if we could adapt, Arwin dynamically, that would be a good thing. I don't know how to do that. I think it's a very difficult problem, and I don't think there's anything that has been presented thus far that gives us a hint as to how this could be practically done. So I think that's a significant issue. We don't live in a perfect world. We're going to have to come up with a solution that's practical. The second quick point I want to make is, and Ketan just kind of made it for me, it's important to be able to work with legacy nodes or nodes that are not optimized. As I understand the RX-based proposal, it's heavily dependent upon the fact that people have optimized their PSNP response time. And I'm not arguing against optimizing PSNP response time, but I don't want to assume that my neighbors have all done this. So,
I'm going to give AC last word in a minute, but I do want to throw out there, because no one's mentioned it. I agree with you that the people haven't talked about where to drive the information from. I personally don't believe it's so hard. My first thing that pops into mind every time we come back to this point is the line card queue depth to the RP, right? I mean, that's a clear indication of how fast your RP is processing things. But whatever, we do need more information there. I think AC, I'll leave it with you. I added 5 minutes to the discussion time, so we do have to cut it when that timer is out.
At 8:09 because I took less time for the status. But anyway, I was just going to say I agree that feedback is good, and they're just using different feedback in the two cases. In one case, it's our window that could possibly, that's explicit. In the other, the transmitter is taking note of the actual behavior of the receiver via, as indicated by the acts that are sent. And I think that's the main difference. I think I also agree that, you know, there's a lot of differences in, you know, how you implement this. You can do things a lot better whether you process every packet to completion or you pull it off a queue and schedule it so you do all the important stuff first. I mean, that's a key one. The other thing, maybe you can talk to, I'll let you talk to this, Chris, is whether or not, you know, when we could, you know, we haven't really concluded, we should probably have an interim when people could do it. I know August isn't a good time.
I think that's a good idea. So just to recap, I think this has been very fruitful, and I think an interim would be a great idea if people are willing to go to it and to do work for it. There's time that people have.
One thing we should take to the list is whether or not we want to do let people, you know, what we should do about experimentation. We'll talk about that.
Yeah, specifically about that one, I'm wondering, you know, going back to the old days of the interop labs over in, you know, UNH or whatever, it would be great if we could get to an apples to apples comparison, right? Like, or get close to one. So, you know, where we joined up the teams. And I guess to that point also, I'm going over time, I shouldn't get the room to combine these two things. But we'll have to take this discussion to the list, I guess. Okay, so up next.
Thanks, everybody. Thanks, both Les.
Yes, thank you very much.
Bruno and Guillaume and Tony P. Everybody who participated. I have to admit, I'm working less on IGPs now. I'm actually working on other stuff. So I was less, even though I'm on the draft, I was less involved than the others.
Yeah, this is great work. This is fun stuff, right? This is real engineering. Okay.
Okay, so it's Tony P. and flood reflection.
It's not sharing. I'm sorry.
You guys have the materials, don't you? All right, I'll keep it really crisp. So just update where we stand with the flood reflection. Next one, please. So I think last time we were showing something was 106, so it's a while. Draft has been adopted. There was 1 or 2 rafts. I think the only, so yes, it's implemented, deployment experience, no interrupts, and we're not aware of any other implementation, otherwise, you know, holler. The one thing that changed in the draft was that what we've seen that the flood reflector should not advertise attach bit because we don't want, you know, this thing to attract L1 traffic towards L2. We got temporary code points, less unified that on a nice value. That's about to expire, so heads up. I think the chairs have to request the extension if we don't get that stuff out as a document. That's the old version you're showing here. Actually, I sent an updated version of this view graph. Now, anyway, so as far as we see, if it could be last called, there is enough information need to implement as far as we see, and you know the discussion of the list didn't bring many questions. Some comments from AC show that we may consider a better tunnel and no tunnel section operationally split. Looking for opinions here. Yeah, and that's pretty much it. So if people think that we need another RAF, you know, with some better operational split for the tunnel, no tunnel option, and maybe some more detail on the no tunnel stuff, but pretty much everything is in the draft, as far as I see, then we can RAF another version. And that's about it. Nothing more from my side.
Okay, Les, you're in the queue. AC, you're in the queue too. Are you meaning to comment?
Oh, I just didn't get out of the queue from the last one. I could say something that I'd like to get more, just to the working group, I'd like to get more people discussing this draft, since it's, it's an experimental draft, along the same lines as TTZ. We have an implementation and everything, and I'd like to get some more discussion on it. I think we have to renew the code points, because I think even if we were to working group last call it today, we wouldn't get it done before the code points expired.
Okay, so I poke you if I don't see the extension stuff, because it's kind of important to us, obviously. Thanks.
Yeah, and I guess my comment, I can't remember if I actually made it to the list or not, to be honest. I'm so sorry, but the tunneling stuff was one of my sticking points too, was with the hand waving done at it, like either pull it out or do more than hand wave.
You mean the tunneling? I mean, the tunneling is very simple.
No, you said you could do it without tunneling, right?
Yeah.
It's like one sentence, right? And it's like, I don't know if it's trying to influence people liking it or, but like just rip it out or expand on it, right?
No, there's information, enough information, I think. But I mean, also AC's observation was that maybe it benefits its own section, and the whole thing pulled together from the couple of places where it explains what the implications are. It's okay.
It basically says smart people could do this, and do this without tunnels. At least the last version I read. Anyway.
Yeah, so the newer version should have more. You basically leak preferences, L2 into L1, and there's like 2 or 3 more sentences where the draft says do not do that. The rationale is, fairly complex, comes from deployment experience. It will work without, but you just don't want to do it operationally to be on the safer side. But okay, so I split it up into 2 section: operational tunnels and no tunnels, and I give it a little bit more explanation. I polish it, put it from the different places in the draft where it's mentioned. Okay,
that would be great. Yeah, Les?
The code points have been renewed. They're good until August 22. You can look in the registry and see that.
Perfect. We can even carry them forward if not. Yeah, perfect. Thanks.
Okay.
Okay. All right, let's go to the next presentation. Shada. Oh,
Hear me?
It is sharing this time. How about that?
Can you hear me?
Yes.
Yeah, so I will present the updates to flexible algorithms, bandwidth, delay metrics, and constraint draft. Next slide, please. We have 2 topics to discuss. One is updates from last revision, and then we also wanted to get input from the working group regarding advertising generic metric for prefixes. Next slide, please. So the changes from last revision are we added a section on applicability to FlexAlgo multi-area case. So basically nothing new. It's FlexAlgo has this FlexAlgo prefix metric. So we just clarified that when FlexAlgo is using a generic metric, what goes in FAPM is a metric that the FlexAlgo is using. So, and that metric could be a generic metric. Basically no change to the protocol procedures, just a clarification. Second point is changes related to max link bandwidth in OSPF. So to compute the metric, we are using maximum link bandwidth in FlexAlgo, and this maximum link bandwidth in OSPF is advertised as an application independent attribute, and it doesn't get advertised in ASLA. So the draft was incorrectly pointing to ASLA, so that change was made. And this change also would need clarifications in FlexAlgo draft, because FlexAlgo says all the attributes must be used from ASLA, whereas in OSPF this particular attribute is not advertised in ASLA at all. So FlexAlgo drafts need clarification, and I have sent some proposed text for that, and request working group to take a look at that. The third one is changes related to generic metric sub TLV advertisement. So this was triggered by some of the comments on the during the working group review, and this is under discussion right now on the mailing list. Next slide, please. It's just a recap of what generic metric is. So this has a concept of metric type and value. Just kind of, instead of defining like delay metric, TE metric, bandwidth metric, and a series of metric, this is a generalization where the TLV carries metric type and value. So there are two parts. Metrics types could be standardized or they could be user defined. So the user defined ones are available for operator to configure and use it as he wants, and doesn't need a IANA code point allocation. So so the concept of generic metric is that any application such as FlexAlgo, SRT, RSVP, or LFA can use it, and it can also get carried in BGP and get accumulated across multiple domains. And it has inbuilt ability to advertise different metric for different applications. So right now the draft has this generic metric sub TLV in TLV 22 and OSPF extended link TLV, and the discussion and we have a discussion going on the mailing list on whether it is to be advertised under ASLA. Next slide, please. Yeah, so right now this generic metric is has code points only for the link metric. That is, generic metric is advertised as a link metric, and we have not taken any code points for the prefixes, and we wanted to see if there are any use cases that would require generic metric to be advertised for prefixes as well. So for FlexAlgo, this is not required because FlexAlgo has already defined on a per FlexAlgo basis prefix metric. So that gets used in prefix computation for FlexAlgo. And even for IGP, we would even for LFA computations on a per FlexAlgo basis, we would use the FAPM prefix metric, and so that is covered. And the authors group is thinking about whether we would need the generic metric type for prefixes. And one of the use cases could be like, let's assume in SRTE, let's say we have red LSPs using metric type 128 and blue LSPs using metric type 129. And let's say we have two remote PEs, PE1 and PE2. And you want to be able to say PE1 is used as a primary for traffic going on red LSPs, and PE2 is a primary for traffic going on blue LSPs. And you could probably do that with advertising loopback metric for the prefixes, metric type 128 to be lower metric for that PE1 for red LSPs and higher for the PE2 for red LSPs. But this probably can be achieved other ways also. So we are looking for input from the working group. Do we really need generic metric type to be advertised for prefixes? Next slide, please. Yeah, we request review and comments, and once we close on these two aspects that are under the currently discussion, probably we would also need an early code point allocation. Yeah, that's all.
Okay, we do have a little time for discussion. There has been a lot of list discussion as well, which is good. I will say, you know, I just went, so to be ready for this meeting, I went back and reread all of the email, and I've talked with AC, and you know, we're not making a rough consensus call now, but it is definitely looking like that ALSLA thing is going the ALSLA way. Maybe just in the future, because you know, there's been some public airing of, you know, like the author, you mentioned the author group is in discussions. If you have a contention, maybe it's better to go to the working group, because it's a working group document now, right? Before you publish it, and it will maybe ruffle less feathers than sort of fiat publishing. You know, your choice. Anyway, just a couple of chair comments. Ketan.
My comment was regarding the need for a generic metric at prefix, especially for the SRT use case that you mentioned. Normally, the SRT paths would be set up to the node, right? Not to a specific prefix. So that is achieved by the generic metric on the link. So I'm not really sure we need it for, and that applies to RSPPT as well. So I'm not really sure we need a generic metric at the prefix level for those two applications. I would suggest that when or if we do have an application in the future that needs it, it can always be added at that point of time.
Yeah, sure. So probably I wasn't very clear with what I meant by the SRT LSPs for the remote endpoint. I can explain that on the list and see if there is interest in such a use case.
Sure, sounds good. Thank you.
Okay, we still have a couple minutes. Shraddha, did you have any questions for the chairs?
Yeah, no, I guess I'm good.
Okay. AC?
Yeah, more discussion on this. So I guess I'll just reiterate what I said on the list. I see this, you know, we spent all this time on link metrics, and now in an existing working group document that does something everybody agreed we needed, if we introduce this generic metric. Now this generic metric, the way I see it, it's kind of ambiguous. You say it's generic, and rather than having application-specific metrics, you have different metric types. I saw examples. This is just from the examples in the email you have. I think it's just, you know, it's kind of an end run, and I don't really think, you know, if we can't get off the dime on this, maybe it should be taken out and we go to a bandwidth metric or something for these bandwidth constraints and done in a separate proposal. Because you know, it's generic. I saw you said, like for OSPF, you said you could put it in the prefix link, extended link attributes, or you could put it back in the TE LSA. So then we'd have another LSA we have to correlate. Would just be a disaster. So as you can tell, I'm not very happy.
I don't know
about
what
it.
your concerns are. I'm not understanding what your concerns are. So for OSPF, are you saying that we should never have it in TE-LSAs, or what's the point?
For flex algorithm, yes, I'm saying we should never have it.
Yeah, so there is no proposal to use it from TE-LSA for flex algo. If you understood it that way, that's incorrect.
We're almost out of time. Can we go to Tony?
Yes.
Hi, so there's no end run going on here. Earlier draft, you know, we had it as a bandwidth metric, and we had some definitions in there about how the bandwidth should be defined. But in looking at it, we quickly came to the conclusion that it's a purely local definition anyway. And there's not a whole lot of reason to mandate that, you know, a particular network operator use a particular algorithm for computing what the metric is. They can do whatever they want. From there, it made perfect sense to have it be more generic. And that's all we're trying to do.
So when you in the draft, when you specifically talk about cases, are you saying that we could move that to sort of like a use case, like this is one way you could use it?
Yes, you could use the generic metric for bandwidth.
Right. Yeah, maybe if we didn't talk about it in the draft so much, it would be more obvious. Ron?
So questioning the words end run. The early statement about this was that it was a violation of 8919, and we pretty quickly agreed that it didn't violate 8919 as the words are written on the page. You know, maybe as the intent of the authors, but not as the words are written on the page.
Yeah, to that point, I didn't find that very compelling, but you're right. If we need an errata or something to clarify, if you know,
I'm not even sure this can be done with an errata. This is an update to the document because you're really changing what it says. This isn't a spelling error.
It's not the intention of the authors. It's the intention of the working group, right? It's a working group document. So, but you're right. We do this then. Right?
The community reviewed the words on the page, not what was in the minds and hearts of the authors.
The working group.
Yeah.
Because I think the working group agrees with what, you know, like Les and others have said. I don't think that the word might be wrong, and we might need a BIS then, as you said, errata might be not enough.
Yeah, a BIS.
If you don't mind a quick break-in, yeah, if you send an errata up, basically what I've got to do to confirm it is go and look at the mailing list traffic and, you know, what the documented consensus of the working group was, and if it's written down one way and it looks like it just got written down wrong, then it's an errata that gets confirmed, and if it's not written down that way and it's just people's opinions, then the errata doesn't get confirmed.
Perfect. So we try for the low-hanging fruit and go for the heavier if we have to. Okay, we are definitely out of time on this now. So let's go to the next presentation. Oh, I didn't have to share again for this one. Okay, Peter.
Yep. Hi, can you hear me?
Yes.
All right. Okay, so I am going to present something new that we came up with Les and Ketan. It's about the IGP event notification. So next slide, please. So a little bit of a background. Typically, what we do in the link state protocols, we distribute the state. Basically, it's a steady state which is being advertised, being in an adjacency state or a prefix being up, etc. And if the state doesn't exist anymore, we simply remove it by the advertising node. So there are certain types of events in the network that doesn't necessarily represent a steady state. It's just an event, and we were thinking if this may be useful for the network operation. So we call this a pulse. Basically, it's a notification which has a very limited lifetime and doesn't introduce any state into the network. And if it does it only for a very limited amount of time. And these pulses may be used to advertise various types of the events, whether those are positive, negative in nature. Next slide, please. So the initial use case that we had in mind when we started this work was basically the case where, you know, the summarization is being used in the network to address the scale in terms of advertising the number of prefixes between the areas or domains. And the result of the summarization is that some of the other protocols that are relying in more specific routes for its convergence, it's basically being lost. We typically use, for example, the BGP peak, where the loopback of the remote PE, if it becomes unreachable, the BGP peak edge is being triggered. But with the summarization, we don't have that visibility. So we would like to get some type of a notification outside of the local area or domain when some of these components of the summarized routes goes away, and we want to do it in a way that it doesn't leave any persistent state in a link state database. So the next slide, please. So what are the requirements for the pulse? First of all, the processing is optional of the information in it. It's decided by the receiver whether you want to use the information in it or not. We want the distribution to be reliable and to be separated from the traditional link state data advertisement. So it is basically being sent independently of the traditional link state advertisement, and the arrival of a pulse must not result in any topology recalculation or route calculation. The basic fact and the first requirement basically on top of the list is the limited lifetime, so it is very short-lived. There is no flushing or purging mechanism for these. These are being basically propagated, used, and then basically destroyed. We need a reliability, so there is some retransmission, but the retransmissions are limited to a very limited period of time, so we don't want the retransmission to actually extend the life of a pulse. And these information are never being sent as a part of the database sync, whether this is on the adjacency bring up or a graceful restart or whatever. These are only sent over the existing adjacencies which are in up state. So the next slide, please. So we define a bunch of new PDUs, which we call the flooding scope pulse LSP and flooding scope pulse PSMP. These are based on the RFC 7356, which is the scoped LSP. We support all the flooding scopes that are currently defined. There is no need for a CSNP because, as I said, we never exchange these as a part of the database exchange. And obviously, I mean, these are new PDEs. So this is not a backward compatible thing. This is completely something new. So if you want to do this, you need a set of routers which would be able to propagate this over the network. The next slide, please. So here's just a comparison to what the flooding speed, what the pulse LSP would look like. So it's similar in nature, but we removed a bunch of the fields in it. And especially, we don't need the remaining lifetime because it doesn't really have the lifetime. The lifetime is by definition use and then discard. So this is just an example how the pulse LSP header should look like. Next slide, please. Similarly for the PSMP, so the header doesn't change, but the pulse LSP entry TLV doesn't have the remaining lifetime, the entry. So it's again very similar, but the lifetime is removed. Okay, next slide, please. So how does this work? What is the update process? So there's a separate instance of the update process for each of the supported pulse LSPs. It is similar to what the RFC 7356 proposes. These are flooded only on the circuits that are participating in a given scope. The pulse LSPs are not retained beyond the time it needs to flood them and eventually use them if you want to use it. We are limiting the retransmissions to a certain amount of retries. We propose 3 by default to have some reliability, but then after that we basically don't continue. We propose to keep the flooding scope LSP in a database for a 0H lifetime, just to minimize the possibility of reprocessing something which has been previously received. Okay, next slide, please. In terms of the generating this, the originator of the pulse LSP should or must remember this, the last sequence number it used for a given LSP, because we are still using the sequence number, to compare the LSP in terms of which one is the new one. We also propose that the originator uses the next LSP ID each time a new pulse information is being advertised. This is basically to prevent the new pulse to refresh the state of the older pulses which has been sent previously. We don't want to refresh them, so we want to really keep them separate and let them die, irrelevant of any other new pulses which are needed to be sent, after that. So the next slide, please. In terms of acknowledging the pulse LSPs, determining which one is new follows the rules used for the regular LSPs. If we receive newer or same version of the pulse LSP, we acknowledge it using the pulse PSMPs. If we receive something that is older, basically we don't do anything. We just basically drop it, because it is going to basically times out anyway. Okay, next slide, please. So, and basically this is the TLV that we are defining to use the pulse LSPs. It's what we call a summary component reachability loss. Pulse TLV, basically when you do a summarization, whether it being on an L1, L2 router or on an ISIS ASBR, when reachable component of the prefix is being lost in the area from which the summarization is being done, we are generating this TLV. This TLV is going to be propagated across the network. It can be leaked. Obviously, we don't want these TLVs to be leaked back into the area from which the summarization is being done. So there is a condition that avoids that. And then when the receiver receives this being in an ingress PE, it may get this notification to the BGP, and BGP may trigger the peak. Obviously, the procedures, what and how this is done, this is a local matter. It is not in the scope of this document, but the idea is that the BGP gets the notification and then it triggers the BGP peak procedure. Next slide, please. And that's it. We would like to get some comments from the working group, whether this is something that the working group is interested in looking at. And that's it from my side.
Are you going to run into patent IPR issues with Snapchat? Just kidding. AC?
Basically, now admittedly, most of the time it's going to succeed, but this is really like a best effort delivery.
Yes.
Yeah.
I mean, there is reliability in it, but it's limited. Yes.
Yeah, it's limited. It's kind of like the next one we're going to see later. It's kind of temporal based on when you got the components of the summary. You're gonna signal the actual. There's two parts to it: the mechanism and then the application of it.
Yes.
To trigger the BGP route resolution.
I mean, it can. Yes.
Yeah.
It can
Yes.
be any application that is interesting in that, and doesn't necessarily.
Right. This is just that would just be the first one, but
yes.
It would work that way. It would take any component that exists at the time, and once you lose that component, you would signal that. Okay.
Wimo?
Very interesting talk. My understanding is that it defines generic procedures and the encodings for distributing the network events. In fact, 10 years ago, I submitted a draft for distributing the abnormal states, but I use the traditional way. I think if we use this way, it will be much better.
Cool.
Okay, thank you.
Aizen? He's muted.
Hello?
There you Yes, there you go.
I think Peter's proposal is another approach for the scenario that's described in the PUA draft. One comment is Peter said the event notification can be used for the positive event. So what is do you have some scenario described for the positive notification, event notification?
Sorry, I didn't really get. Can you repeat? Or
You know, you.
It may not come through the second time either. Your mic is sort of going in and out.
Yeah.
It's kind of hard to hear. Maybe you could post your question to the chat room and we could echo it back maybe even after the next presentation, like, because I think we will have some slop.
Yeah, okay. I will present question on the mail list. There are large echo for the voice.
Okay, well, the interesting new work. Let's get some discussion on the list on it. I do have the question. This is related to the next presentation. Is that right? Or maybe I got that wrong.
It's the prefix unreachability stuff.
Yeah, that's what. That's
yeah. So
They do sound
okay,
very
so,
familiar. I'm similar. I think. Sorry, Steve speaking.
Yeah. So the one of the use case that we have is this one, and this was the first one. So it is related in terms of the use case, but we use a completely different mechanism, and what we specify can be used for something, more than that.
Right. It's more generic. Exactly.
Yeah.
Okay. All right. Great. Well, keep that in mind, everybody, while we watch the next presentation. Ian?
All right. Thank you, guys.
Thanks, Peter.
All right. So my name is Guillaume Mishra with Verizon, and I'm providing an update for prefix unreachable announcement PUA. So as Tony gave the update for the, sorry, Peter, on the last draft that we went through, this is a very similar mechanism that we've had quite a bit of discussion on the mailing list. But it basically works very similar. The mechanism is completely different, but it works basically on the component. So if you have a transit core where you have the area broken up into areas, so either OSPF areas or ISIS levels, and you're doing summarization and you're summarizing the next hop attribute, for the edges, your egress or ingress PEs. When those components, so when you're summarizing all the /32s, and instead of having to flood them, you're doing a summarization. When those components go away, from a link or node failure, what this draft does, kind of in summary, it basically detects that via an advertisement and control plane update, and then it forces the control plane to converge. So it's an update to the control plane, so the control plane converges, and then the data plane, no change to the data plane, and the data plane follows the control plane and it converges as well quickly, just based on a component failure. So it is like an event notification, similar to the last draft, completely different mechanism, but it from that detection, it forces a convergence. Next slide. Thank you. So the PUA mechanism. So basically, upon receiving a node or link failure from a prefix, that's within a advertised summary from an ABR going between within a domain from, let's say, ingress PEs towards an egress PEs within from an ABR performing a summarization towards an egress point. So we generate a new summary address, but with the failure prefix associated with that, it sets that information to a null zero null information to null. So basically, and that's really the capability where it's actually flooding that. So when that linker node goes down, or the next hop attribute goes down, that prefix is set to null, and it's forcing that that convergence to happen at the control plane, and then the data plane follows that. So for ISIS, what we do is we use the IPv4, IPv6 source router ID sub TLV defined in RFC 7794, and with OSPF we use the prefix originator sub TLV defined in the draft OSPF prefix originator. And then the flooding mechanism is exactly the same. There's no change in the flooding mechanism for both OSPF and ISIS. Next slide, please. So the updated action based on the PUA message. So for the node failure scenario, when the node within an area receives the PUA message from all its ABRs, it will trigger the switchover. So that's the switchover is basically that component prefix. So let's say that linker node goes down, that egress PE node goes down. It actually that prefix for that, let's say you're doing a next hop self on that P, and that loopback 0 goes down, but the node is down. Now that prefix is set to null 0, and now you're forcing that switchover to happen immediately from due to that summarization. So now you're not waiting for convergence. Convergence happens instantly onto the alternate path. So for link and network partition scenarios, when only some of the ABRs can reach the failure prefix, the ABRs that can reach the prefix should advertise a specific route to the PUA prefix. And it's a similar kind of negative. I think we mentioned it's similar but different, but I guess you can draw some analogies to the Rift. Rift work group and how the negative advertisement happens. Next slide, please. Thanks. So conclusions and further actions. So we have had a lot of discussions, and we've presented this on the IETF a few times. There have been, I think the goal here is really try to get more clarification on the process and procedure and how the PUA mechanism works and what actually is changing. So with the changes, it's really control plane. There's no change to the data plane, and it's really a detection mechanism, detecting the component prefix, very similar to the previous draft that what we went through. But it's really the detection mechanism, and from that detection, forcing the control plane to converge, and then the forwarding plane to follow that. This does, because it's a control plane update, all the nodes within the area, they would require an update because they're all acting on the failover capability to set that prefix for the component to a null 0, so it's to force the control plane to converge. So it does require an upgrade, and that's something that we do have to update in the draft, because that, I think A said notice that, and so we'll get that fixed in the next update. Next slide. Thank you. The next draft I'll be going over just some quick updates on is the passive interface attribute. Next slide, please. So what this proposal is to solve is, so this is something as well, and I think Ace had mentioned that, I think probably a few times and maybe others, it's something that we will fix in the draft. So passive interface is a implementation specific command, and so we will replace any references to the passive command and change that to stub. So thanks for those comments, and we'll get that fixed. So what this draft does, and the goal is to provide any cases, any use cases where you have a stub LSA. So it's really like the passive command is implementation specific, but when you have a stub LSA with no neighbors, so that's really tracking that interface, so that link that doesn't have any neighbors, and it could be an interface within a data center, an inter-AS boundary, and then I guess it's a new use case with edge compute scenario with 5G edge compute, the draft link there, where we don't have any neighbors, so it's an interface that's made passive with no neighbors, so it's a stub LSA. So being able to track that and update either for a BGP controller or PCE controller, be able to differentiate interfaces that are passive from interfaces that have neighbors, I think, and that's with the BGP LS or BGP controller. Next slide. So the OSPF v2 extension, I think we had a variety of different ways where we're going to do this. I guess the update, I think initially we had it in the base OSPF v2 and that was fixed. So now it's in the TLV based OSPF v2 update. And I think initially we had it using the prefix LSA and we changed that because I guess the passive interface being link specific and really was what we wanted, topological versus prefix based. So using the OSPF v2 extended link opaque LSA versus a prefix LSA and the same for OSPF v3 and ISIS. So what we propose is defining a new OSPF v2 extended stub link TLV. And this has been updated in revision 8 and with a link type and metrics field with this newly defined TLV. So the link type field can be used to indicate subdivisions of the passive interface and other future potential uses. And in that field, there's a few different options and we can expand on it for that field. So let's say like 1 is AS boundary, 2 loopback, 3 VLAN, and then a variety of other future extensions that we can add to that. Next slide, please. So for OSPF v3 and ISIS, it's similarly done using the, so it's, with OSPF v3, we define a router stub link TLV to describe the router stub interface. And the TLV would be contained within the eRouter LSA. And then ISIS would be a new top level stub TLV. And then the similar options that we have for the link types, for the various link types that would be supported. And I think for now, like in the draft, we would have AS boundary, loopback, VLAN, and then future extensions that we can, extensibility that we can add to the draft. Next slide, please. So newly defined sub TLV. So once the newly defined sub TLV describe the IP address information that's associated with the passive interface is defined. Sub-object is defined within RFC 209 extensions for RCPTE, and then proposed one independent registered code point, IN allocation for the stub link attribute, which can be referred by OSPF v2 and v3 and ISIS. So all three of those would have a new IN allocation code point. Next slide, please. So for further plans, any comments? I think we have had a lot of comments. So we'll probably spur this up on the mailing list again, and get more feedback. We appreciate all the feedback that we've gotten so far on this draft and the PUA draft from the chairs as well as folks within the work group. So much appreciated. We've added a new co-author to the draft with ETE, Xingtung Sun. Welcome. And we'd like to, I guess, the next steps, ask for an adoption poll for this draft if folks feel that this draft is ready for adoption. Thank you.
Casey, you're in the queue.
I think Gian and Ajahn understood my comment that I don't think we already have, we have links for things that are topologically significant to the IGPs, and we have prefixes for local addresses. And I don't think we need, for addresses that we're advertising local, the inter-area prefixes. I don't think we need this stub link explicitly. You could take this single stub link type or whatever you want to call it and add it to a prefix if you really needed it. Now the IGP certainly doesn't need it, but so you want us to carry this solely for other applications. I mean, other use cases. And I mean, for one TLV, I know we've done this before, but where we have optional TLVs that we've had, we have things definitely have sub TLVs that we carry for prefixes that aren't used explicitly by the IGP. So that's kind of a moot point. But to invent a new construct, the stub link, and then you realize, oh, I need the address of this as well. So we're advertising the address of it separately. then we're advertising the prefix that we use for the route computation. That's what I think is wrong. And I know we disagree on this, but that was my main comment.
So that's as a working group member, I would imagine, right?
Yep. And as a co-chair, I'd like other people to read this, not just me.
Yeah, and so I just before we ran out of time, I wanted to throw out there that we do have adopt as a working group document on the slide, so we should speak to that. Do you think that
there was a request?
Still,
that's because there was a. I don't think so. That there was a request. I had a question mark.
No,
but
right. I'm saying they're asking us. So I'm saying we should reply, and I guess our answer is probably going to be let's have some more discussion on the list.
Yes.
Yeah. Maybe not there yet, I guess is.
Yeah. I think Ijun's in the queue. I don't know, Ijun, you want to chime in on anything? I guess comments on this route?
Yep. Ijun.
If you can get your mic working.
Originally, we have put the information within the prefix TLV, but after discuss on the main list, there are some we change it to the sub link. So I think if I say such information should be associated with the prefix, we will read the discussion before and find whether it is suitable or not. Okay.
Yeah, speaking as working group member, I think once you had to add the address to the stub link and you're advertising that prefix two different ways, I mean, actually you're not advertising the prefix, just the address, but advertising it two different ways, that would be a good indication that this is not the right way to encode it.
Okay, we're out of time. So just wanted to give a final thoughts. I think that the discussion was really good at the beginning of this. And I think that if people are willing to and have time to put more work into it, Bruno less, that we should maybe look at doing an interim. Yeah, that's all I had to say. Oh, you're muted.
Yeah, I think we should do that right away.
Hello?
Okay, great. Well, we'll have to see whether in the next 2 weeks we're going to have another virtual or not, probably. But thanks everybody for participating, and see you next time.
Thank you.
Thanks.